welcome back. We've been diligently estimating population parameters. We've got one more set to look at. So far, we've made population proportions with a best point estimate of a sample proportion, or we've also looked at how to find out how many people to ask, right? We've looked at sample sizing. We did that also more recently with population means. We did it in two different ways using either z-scores or t-values, depending on if we knew what the population standard deviation was or wasn't. Or if we knew what it was, we would use the z-score, or z of alpha over 2. And if we had no idea and we just had our sample to fall back on, we would use t-values. Well, now we're going to start looking at variance. Things are going to get a little messy here, but bear with me. But because the process will stay mostly the same. So we're going to look at population variance. We're going to look at variance because, hey, if you got variance, you just square root that thing, you got standard deviation. Here's what we got so far. Here's all of the processes so far. Remember, we decide on our confidence level, which is going to in turn give us our critical value. Granted, this last one, this t value, depended both on confidence and on sample size. But once you had your best point estimate and you had your confidence level, that gave you critical value, you found your margin of error, and then that helped you construct the confidence interval plus or minus e away from your best point estimate. So fingers crossed, that's going to work for variance. Well, so far so good. We're going to use our best point estimate to be our sample variance, which is, of course, just the square of our sample standard deviation. Okay, so far so good. Let's look at critical value. Oh boy. Bad news part 1. That's a new type of critical value. We cannot use anything we've used so far for variance. And bad news number 2, there is no margin of error. There is no margin of error for variance. I'm sorry. There just isn't. And why is that, you might wonder? Well, to have an error margin, you have to have symmetry. When you have symmetry, you can make things like we've been making, like 95% confident that mu is somewhere between x bar plus or minus e, or x bar minus e less than mu less than x bar plus e. Right? We can make those statements using the symmetry inherent in our systems so far. Right? We looked at this in 6.3. We looked at it more recently too. Sample proportions formed a normal distribution that was centered around the population proportion. So, hey, we made that error margin, and we could build from there based on our sample. Means, same deal. We had a normal distribution. The mean was the center of that curve. Great. But if you remember, variances, and by extension, the standard deviations are the odd ones out. They are not true normal. They are skew normal. Actually, they're called their own thing. They're called chi-squared. They're special like that. Oh, by the way, this Greek letter here, this is not some script X. This is the letter chi in Greek. C-H-I, pronounced chi. And since this is not symmetric, we don't get error margins. We can't build the intervals like we have been. What we have to do instead is use this formula right here. Note that your lower bound has one set of critical values, and your upper bound has another set of critical values. That said, process is otherwise the same. You're going to find your sample variance. You're going to decide on your confidence level. And I think these depend on sample size as well. You'll look up your critical values, and then you'll use them in these formulas, which again, blessedly, we don't have to memorize, and that will construct our confidence intervals that way. So in the next video, which I think might be the last video for right now, is just where to look these up. And I'll see you then.